This is the second lecture on Hamiltonian chaos, and in the previous lecture we had discussed the Poincaré-Birkhoff and Kamm theorems. The Poincaré-Birkhoff theorem and the Kamm theorem address the fate of Hamiltonian systems when non-integrable perturbations are added to an integrable part. When you have an integrable Hamiltonian, and it's denoted here by H naught, H0, then all the motion lies on tori, because this is integrable and the entire phase space is covered by tori, each of which is indexed by particular values of the actions. To this integrable part, if we should add a non-integrable term such that the whole Hamiltonian is now non-integrable, then the Poincaré-Birkhoff says something about those tori on which the dynamics was periodic, namely the rational tori. What the Poincaré-Birkhoff theorem says is that these rational tori are destroyed and they leave behind a set of 2 times s times k fixed points, that is an even number of fixed points, alternately being stable and unstable. So, you have a stable fixed point followed by an unstable and so on and so forth. There is an even number of them, and how many of them depends on what's the winding number, or what are the ratios of the two frequencies on which correspond to the two different directions on this torus. The example over here, and many of the examples we will talk about, are for 2 degree of freedom Hamiltonian systems, and that means that the sections, the Poincaré sections that we are examining, are 2-dimensional. So, starting with a rational torus marked here, once you add this non-integrable perturbation, this rational torus evolves in a particular way, so that all that we are left behind are these fixed points, 2 of which are unstable and 2 of which are stable. The KAM theorem addresses the quasi-periodic tori, namely those tori on which the frequency ratios are irrational, and this is the vast majority of tori even in the unperturbed system. What the KM theorem says is that if the system is sufficiently nonlinear, that is to say H naught itself is sufficiently a nonlinear system, if the torus is sufficiently irrational, by which we mean that the ratios of the frequencies omega 1 by omega 2 is sufficiently irrational or is poorly approximated by rational numbers, so that's poorly approximated by rational numbers, and if the coupling is sufficiently small, then the torus will survive in the perturbed system. Or in other words, there will be an invariant torus of the perturbed system that is in a sense close to the torus of the unperturbed system, and as the perturbation term vanishes, these will merge into each other. The implication of the KAM theorem are best understood for a 2-freedom system, and we will turn to that now. If a 2 degree of freedom system or a 2-freedom system is integrable, then note that when the degrees of freedom are 2, the phase space dimension is 4, it is a 4-dimensional phase space. If there is a Hamiltonian and you have a conserved quantity like the energy, one conserved quantity in this 4 dimensions automatically constrains everything to a 3-dimensional energy shell. And in this phase space, we have tori if the system is integrable. A good example is given by a 2-degree of freedom harmonic oscillator. So I write down the Hamiltonian as a half px squared plus py squared plus a half x squared plus y squared. And rearranging the terms, you note that this is written as a harmonic oscillator in the x variable and the harmonic oscillator in the y variable, which are uncoupled from each other and is separable. And because it is a separable system, it is also integrable. In action angle variables, you can easily show that in the action variable Ix and Iy, H naught just becomes the sum of Ix and Iy. If to this we were to add a non-integrable perturbation, on a Poincare section, what we can see is the following. The rational tori will break up to form chains of fixed points, alternating elliptic and namely stable fixed points and hyperbolic or unstable fixed points. You can see that over here, where you've got the elliptic fixed points over here and the hyperbolic ones marked out by x's. Different rational tori seem to have broken up over here. So there's another rational torus that is broken, another one over here, and one over here. For this outermost ring of stable and unstable fixed points, we've also drawn in the stable and unstable manifolds of the hyperbolic fixed points over here. And as is typical in such systems, it is possible for the stable and the unstable manifolds of different fixed points to intersect. And because they have intersected once, they must intersect infinitely often, giving rise to this tangle over here or over here. Around every hyperbolic fixed point, there is a hyperbolic tangle. Some of the quasi-periodic tori are surviving, and these are the solid curves that you see over here. Recall that this is the Poincare section of the flow from the 4-dimensional system to the 3-dimensional energy shell, and this is a slice across the 3-dimensional energy shell. The tori that survive are often termed as cam tori. Poincare himself in 1892 was aware of this image, even though he couldn't quite draw it. He writes in the New Methods of Celestial Mechanics, is the translation. He says, the intersections form a kind of lattice, web or network with infinitely tight loops. Neither of the two curves, the unstable manifold of the hyperbolic point or the stable manifold, must ever intersect itself, but it must bend in such a complex fashion that it intersects all the loops of the network infinitely many times. One is struck by the complexity of this figure, which I am not even attempting to draw. Nothing can give us a better idea of the complexity of the 3-body problem and of all problems in dynamics where there is no holomorphic integral and the canonical perturbation series diverge. The absence of a holomorphic integral over here essentially refers to the fact that the system is non-integrable. So, to the system of 2 harmonic oscillators that we had started with, if we now add this particular perturbation, which is y times x squared minus y squared divided by 3, one gets a very famous non-integrable Hamiltonian system that was first written down by Michel Hénon and Carl Halleys in the Astronomical Journal in 1964, very shortly after Lorentz's study of the Lorentz attractor in 1963. This Hamiltonian system has in many ways played the same role as the Lorentz system the Lorentz system plays in the study of dissipative systems and dissipative chaos. The Henon-Hiles Hamiltonian plays a very similar role in Hamiltonian chaos. For this system, there is only one truly conserved quantity, and that is the total energy. A short calculation will show you that the potential energy, which is these terms x squared plus y squared and this additional perturbation term, all this is purely potential and all this is purely kinetic. This potential energy has triangular symmetry, and all the motion is bound if the energy is less than 1 by 6. In 1964, Henon and Hiles made calculations and they were able to see orbits in this particular system, and they found two different kinds of orbits. One was a set of quasi-periodic tori, and here are images of these quasi-periodic tori with the potential energy surface drawn over here. So, this is in the x, y plane. Here are images of tori, and you can see the very smooth, very well behaved, well ordered curves over here. What is distinguishing about the tori are these caustic curves where the trajectories all focus along certain points, and this is very typical of motion on a torus. Note that this is a motion on a torus in a three-dimensional space which is being projected now onto 2. But what you see, these caustic curves are very characteristic and are a way of identifying toroidal motion. In contrast, you have a motion that seems to be near a torus for a little while, and then it just seems to escape and go all over the place. And this is an orbit which is termed chaotic because you can compute the Lyapunov exponent using the methods that we have discussed earlier, and we find that you have a positive Lyapunov exponent, but again you have chaotic motion in this Hamiltonian system. If we were to compute surfaces of section as a function of energy, and these are images taken from Henon-Halleys' original paper, again recall that we are doing a surface of section of a 2-freedom system, 4-dimensional phase space, 3-dimensional energy shell, and you are taking a surface of section to bring the whole image of the motion onto 2 dimensions. When you have tori all over the place, then when you cut through this set of tori, you basically find nested tori one inside the other, and at very low energy, E is 1 by 12, you find that the motion is completely covered by tori everywhere. The image of the tori on the Poincare section is a closed curve. So, wherever you look, you find closed curves. At a higher energy of 1 by 8, you find that now some of the rational tori have broken up, leaving behind the stable and the unstable points. Surrounding the stable points are also these tori, these small islands that you see over here, and the unstable points would have been somewhere over here, but because of the heteroclinic tangle that we saw in the earlier picture, you don't see those hyperbolic fixed points anymore, and what you have is just the image of chaos all over the place. You have the remnants of Cam tori, you see some of them over here. As you increase the energy even higher, and this is essentially the highest energy for which all the motion is bound, you find that the phase space is really largely covered by chaotic orbits, that is, points on an orbit that don't follow any curve, although there are some cam tori, you can see them over here and here and here, but by and large the entire motion is dominated by chaotic dynamics, and what we see is chaos everywhere, chaos in a limited region over here, and mostly tori everywhere over here. Integrating equations of motion in Hamiltonian systems is not particularly difficult because you know the Hamilton's equations for the system, but it is possible to integrate these equations for much longer times if we work with mappings rather than differential equations. In discrete dynamical systems, and a lot has been studied in this area, the analog of Hamiltonian evolution is area preserving transformation. Recall that in 2 dimensions, early in one of the lectures of this course, I had shown and discussed that the change in area in a discrete map is essentially the determinant of the Jacobian matrix. So, area preserving maps in 2 dimensions resemble the dynamics on the Poincaré sections of this 2-freedom system quite faithfully. Michel Henon again in 1969, and actually also in the Henon-Halleys paper, introduced mappings to mimic Hamiltonian dynamics. And here is one such map which shows some features of the dynamics particularly well. This is a 2-freedom map. So, you have x I plus x and y, and as the mapping relates x I and y I, namely the value of x and y at the ith point in iteration to the value at the I plus 1th point in iteration through this particular relationship, and you can easily verify that the Jacobian of the transformation has determinant 1. This dynamics is very interesting and very similar to the Henon-Halleys surface of section that we saw for different values of alpha. So, here is the case where cosine of alpha is equal to 0.8, and you find that all the points in this region are lying on smooth closed curves, very much like the torus motion that we had in integrable systems. The mapping is not integrable by any stretch because there you can see that there are orbits that move away, but certainly you can see the image of toroidal motion over here. As you change alpha, and here the change is to cosine alpha is equal to 0.4, you find this familiar image of stable and unstable points alternating on a ring. So, here you have an elliptic fixed point, a hyperbolic fixed point, an elliptic, hyperbolic, elliptic, hyperbolic, and so on and so forth. Okay. Then there are orbits that escape to infinity, and that is a feature of this map. Very interestingly, you can also see the effect of the heteroclinic tangle. Here is an image of the mapping for cosine alpha is equal to 0.24, and here you find that the elliptic fixed points, you see them really at the center of these islands over here, and the hyperbolic fixed points which you see over here. Now, the hyperbolic fixed point, you can't see it itself because it is an unstable fixed point, but you can see the effect of the heteroclinic tangle if you zoom, and this I think is a zoom of this particular point over here, of this point over here, this gets zoomed out, and what you see is that the image of this heteroclinic point is somewhere over there at that location over there, and then every point over here you see is really an image of this heteroclinic tangle. You can see cam tori, you can see other chains of islands, and you can see that between these chains of islands also there are heteroclinic orbits and the tangle over here. So, there is tangles everywhere. This is very much an image of what has happened to the rational torus that was surrounding this point, having broken up, and then it has resulted in all this chaotic dynamics. One can study these maps, many of these maps, but the standard or the Chirikov-Taylor map has played a very important role in a lot of discussion on Hamiltonian chaos. This is another two-dimensional mapping in, loosely speaking, action angle variables, except that now we've got this is like a momentum variable and this is an angle. So this actually can be shown to come from a Hamiltonian system, which is a time-dependent Hamiltonian system. And here so the potential energy, which is k cosine theta, that actually acts only at times, at integer times. So whenever the time is equal to n is 0, 1, 2, 3, etc., integers, this potential energy acts up because of the delta function. And between the kicks, the motion is purely ballistic. It is just a half p squared. The Hamiltonian is a half p squared, so you just have got straight motion. If you were to write down the corresponding Hamiltonian equations for p dot and for theta dot from this Hamiltonian, you would, and then you proceeded to discretize it, the following equations emerge. This is a mapping now, and this mapping is actually a fairly faithful representation of this dynamics, because the potential energy acts only at integer times. So the momentum, in a sense, can only change at integer times, and the angle evolves smoothly between the kicks. So there is no so that's this evolution. Between the kicks, the evolution is ballistic. Now, this standard map describes typical behavior of area preserving maps with a divided phase space. I am going to come to that on the next slide. And it is of great relevance to particle dynamics and accelerators, also to microwave ionization of Rydberg atoms, numerous other very practical, realizable experimental systems. The dynamics can be, of course, integrated very simply. You start with a whole set of different initial conditions and you just evolve them under this map. And what you see is, as a function of k, the dynamics, the image of the dynamics is very different. This map is defined modulo 2 pi. So all the variables are just divided by 2 pi in this diagram over here. So everything, this is theta going from 0 to 1, right, and this the images themselves are taken from Chirikov's paper. For low k, k is equal to a half, you find that if I start with an initial condition over here, it will trace out a smooth curve that traverses this square from one side to the other. Most of the curves are smooth, joining joining it back onto itself. Occasionally you have these islands that you can see over here. These are remnants of rational tori, and one must remember that k not equal 0 is immediately a non-integrable system over here, because if you go back and look at it, if k is equal to 0, this term does not exist, and Pn plus 1 is a conserved quantity, because Pn plus 1 is just equal to Pn. As you increase k to this special value, you find that this is the point where orbits are they have this special feature that an orbit starting over here, let's say, remains within this particular band, and orbits that start over here remain within this particular region. Even though they are completely chaotic, they don't traverse this square from top to bottom. So, this is the divided phase space that we referred to in the case of the standard map. And the reason is that there is a curve which is traversing the square from left to right, which in a sense prevents traversal of orbits from bottom to top. At this value of k, the last such curve just disappears. Notice that this is a curve that is traversing from left to right, as is this, as is this, as is all these. So, for small k, you have a very large number of curves that traverse from left to right and prevent top to bottom motion. At k equals 0.97 whatever, you find that the last such curve has just disappeared, and for larger k, now orbits can move freely from top to bottom or from left to right. They can just move everywhere, every which way, because there are no curves that bound the motion to remain in any particular region. There still are cam tori even at the higher nonlinearities, and this is a feature of many chaotic systems. Okay. The standard map has been very important because it is possible to calculate this last value of k analytically. This is in a sense helping people understand exactly how widespread chaos comes to be, what are the things that go into the breaking of tori, and how the KAM theory works in practice. Another class of systems that has helped in the understanding of chaotic dynamics in Hamiltonian systems particularly has been billiards. Now, billiards are a generalization of the particle in the box problem, where basically you have a particle that is moving freely inside an enclosure, and when it comes to the edge of the enclosure, you find that it gets scattered from the edge of the enclosure with the angle of incidence equal to the angle of reflection. Right. So, the potential energy inside the box is equal to 0 and the potential outside is infinity. And some billiards have been studied in great detail, helping us to understand the difference between chaotic and non-chaotic dynamics. What is shown over here is a circle billiard. So, you have a particle inside a circular enclosure. This is a particle inside a square, except that there is a scatterer in the middle of this square. So, the particle not only reflects from the boundaries of this enclosure, but also it reflects from this scattering element over here. Right. This is known as the Sinai billiard, and this is in the shape of a stadium, and so it is called the stadium billiard. Now, billiards can be regular or irregular. In particular, some billiards are integrable, and the number of constants of motion are equal to the dimension of the configuration space. Now, in 2 dimensions, some familiar billiards are the rectangle billiard, which also is a real physical billiard when you play the game, a circle billiard, and the elliptic billiard. These all turn out to be integrable. What I have shown over here are orbits inside a circular billiard, and you can see that the circular billiard now the caustics of the motion, that is to say the shape which is formed by the envelope of the trajectories, the caustic of the motion is another circle. Likewise, for an ellipse, there are some orbits that that have a caustic of an ellipse, but there are also other orbits, many other kinds of orbits. In particular, there are orbits whose caustics form a hyperbola. And these 2 points over here are the foci of this particular ellipse. There are orbits in addition that will just bounce back and forth along that particular point over there. So, there are many different kinds of orbits that are possible. In contrast to the integrable billiards, there are non-integrable billiards as well, and the stadium is an archetypical example. A typical orbit in the stadium billiard is completely chaotic. It just goes all over the place. In fact, if you give enough time, it is also ergodic. It will go over the entire space available. And this is in sharp contrast to let us say something like the circular billiard, because wait however long you want, the central region is never going to be filled in by any orbit. In addition to a chaotic orbit such as the one that is shown over here, we also have a host of periodic orbits. For example, there is one that bounces back and forth between the midpoints over here. There are an infinite number of orbits that will bounce back and forth between these walls. In fact, they have a name, they are called the bouncing ball modes. Then you have an orbit that will just bounce from the midpoint of this side to this side to this side to this side, like a diamond over here, and an orbit that looks like a Z and a figure of 8 and so on and so forth. These are all periodic orbits because they retrace themselves. Nevertheless, all of them are unstable. And this is a characteristic feature of these kinds of systems. Right. This brings me to the topic that I want to discuss at the very end of this introductory set of lectures, because a lot of physics deals with classical dynamics, of course, but more relevant question to ask is to do with the quantum mechanics of such systems. Does the nature of the classical dynamics have any impact on the equivalent or the related quantum phenomena, on the quantization? Now, part of the reason for asking a question like this is historical, because there is a long tradition of associating classical orbits with quantum states. In fact, in most early treatments, or the earliest kind of treatment that the typical student is exposed to, is Bohr-Sommerfeld quantization, where a specific kind of orbit is associated with a quantum state. Or further down the line, when you see the semi-classical WKB method, that is also a way of associating classical and quantum mechanics. What is done in those cases is that the classical system is effectively expressed in action angle variables, and correspondence is made between integer values of the action or specific half integer values or any other, there are some other cases. But correspondence is made between the integer values of the action and specific quantum states. Now, in order for that to happen, you must have action angle variables, and that must mean that you have tori. But we know that most systems are non-integrable. This is the discussion we have had in the last 2 lectures. And if there are few tori or no tori in the phase space, then there are no action variables that you could construct easily anyhow. However, you can take a completely different view of quantum mechanics and say that the quantum Schrödinger equation over here, h psi is equal to e psi, can always be solved. Even if it's a numerical solution, you can always solve the quantum equation over here and get the associated eigenvalues and eigenfunctions. Now, this led in the 1970s to the question, are there regular and irregular states? Namely, we know that there is regular and irregular motion in Hamiltonian systems. The regular motion is associated with tori. The irregular motion, the chaotic motion, doesn't have tori. Is there some connection between states that are associated with tori, and are there other kinds of states that are associated somehow with chaotic motion? Now, this was an early discussion of the problem, but over the years there's been a lot of work in this area, and these ideas have been greatly refined, especially because there are a whole lot of applications. But one aspect of the difference between quantum mechanics of regular systems and irregular systems was identified very early, and this has to do with eigenvalue spacings. Looking at the spacings of many quantities has been an area which has been of interest, and here is an image from which I picked up from the net from somewhere, which shows a lot of different levels. Okay, over here is just a bunch of lines that are equally spaced. These could be the energy levels of a harmonic oscillator, for example, equally spaced energy levels. If one just had purely random levels, then this is what a typical realization of random levels looks like. If I take the periodic spacing over here, the harmonic oscillator, and then just jiggle it a little, add a little noise, you get something that looks like so, begins to look like a barcode. But right next to it is the eigenvalue spectrum, the levels of a radioactive nucleus, erbium-166. These are the nuclear energy levels of erbium-166. Here are a set of eigenvalues of a matrix which is got completely random entries. It's a symmetric matrix, but it's got completely random entries in one half of it, and here are the eigenvalues written down so. This is the Riemann zeta function, and here are the zeros of the Riemann zeta function starting from the 10 to the 22th zero upwards. So you can see how they are spaced, and here finally are 100 consecutive prime numbers starting from 103613, and that's what the spacing looks like. Of course, these are all normalized such that you have 100 levels in each of these columns, but you can see that the kind of system and the kind of levels seem somehow to be related, or rather it's very characteristic. Here is a harmonic oscillator, absolutely equal, random, and various levels of correlation between these different kinds of levels within the same system. Right? Where do chaotic and non-chaotic systems fall in this classification? And note that chaos or lack of regularity or integrability and chaos are terms that come from classical dynamics, and we are asking the question of what happens to the quantum mechanics of such systems. Well, attention was drawn largely by Michael Berry and by Ian Percival to the spacings distribution in those days, and it was proved that for completely integrable systems, the eigenvalue spacing distribution is Poisson. Leave out harmonic oscillator systems because they are exceptional, but if you take a typical integrable system, you would find that the eigenvalues have got a Poisson distribution, which is basically just a decaying exponential, and the highest probability is to have a spacing of 0, or levels are clustered very closely together. For non-integrable systems, on the other hand, there is a belief that they have the same distribution as random matrices. In some sense, the complexity of the classical dynamics shows up in matrix elements that are completely random. And this goes back to an observation, a conjecture by Eugene Wigner on that the eigenvalues of random matrices should provide a good model for nuclear energy levels, at least as far as the statistics of the levels were concerned. Wigner surmised that the distribution would be something like this. This is basically a Gaussian, but it's shifted, it's multiplied by S. So this actually is a distribution that looks something like so. Okay. So you have a distribution which is Poisson or just a decaying exponential or a Wigner distribution, and the conjecture was that for integrable systems one would find Poisson, for chaotic systems you would find the Wigner distribution. Well, if you take a circle billiard, it's an integrable billiard. You can write down the Schrodinger equation, and it's in 2 dimensions. So you just have this is the kinetic energy, and this is the eigenvalue equation. And the boundary condition, of course, is that the wave functions have got to vanish on the outer circle over there. And this is a well studied problem, and it can be solved exactly. The eigenfunctions and the eigenvalues can be computed exactly, and they are related to zeros of the Bessel function. Now, if you calculate about 100,000 such levels in the circle billiard, and you form a distribution, here is a histogram of the distribution. It follows the Poisson distribution very well. So here you find this is an experimental result, if you like. Here are 100,000 levels of the circular billiard, and it follows the Poisson distribution rather well. If you take the Sinai billiard, as Boigas, Giannoni and Schmidt did in 1984, then you can again solve the Schrodinger equation in this particular enclosure. Here there are 2 boundary conditions to be followed. The wave functions have to vanish on the square, and they have to vanish on the boundary of the inner deflector. This is a completely chaotic system. There are no periodic orbits that are stable, and so there is no question of having some mixtures of tori and chaos. So the eigenvalue spacings for this, they really conform to the Wigner surmise, which you see over here is this particular curve that has been drawn, and again you find a histogram that has been drawn. The Poisson distribution is this exponential curve that you see over here, and the actual distribution is nothing like it. Boigas and company did not actually solve it in this enclosure. They solved it in a quarter of this enclosure, which is essentially the same features of chaos in all the orbits. So it seems that the eigenvalue distributions, the spacings distributions, follow these 2 extremes of in these of the Poisson distribution on the one hand and the Wigner distribution on the other hand. For systems other than billiards like Henon and Halleys, the phase space can have a mixture of tori and chaos, and the statistics tend to be more complex, but it's quite understood in which way they are more complex. Now, this is a subject which has really progressed way beyond where it started out in the 70s and 80s, and people have looked at the eigenfunctions, the nature of the eigenfunctions in different kinds of chaotic billiards. Here are just some images taken from the web on that. There are many open issues in Hamiltonian chaos, and particularly in the area of quantum chaos, and the current frontiers are much further along than looking at eigenvalue statistics, although this continues to be, like many other problems, something of abiding interest. Thank you.